Here we go. In 12.4, we're going to learn things called complex numbers. Complex numbers are the imaginary numbers and the real numbers that you have been dealing with. So every kind of answer we have had up until now have been in the real number solution. The negative numbers, the positive numbers, the zero, all those, plus the fractions, plus the square roots, those are all real numbers. Where we get into complex numbers is we're dealing with imaginary numbers. What is imaginary? What doesn't really exist? It's the square root of any negative number. So what happened a long time ago was somebody invented, some mathematician or just somebody like you sitting there thinking, why can't we square root a negative? What if we could? And this person, whoever it was, I do not know who it was, invented the complex number system. They thought, why can't we square root a negative? And the reason you cannot square root a negative is because something times itself needs to equal a positive. There was no way for something times itself to equal negative. But somebody asked, what if that existed? Let's call that an imaginary number I. What if I was the square root of negative 1? And what if a negative root 1 and a root of negative 1 and a root of negative 1 multiplied together equaled a negative 1 by definition? What would that look like? And these are the problems that you can do with this type of stuff.
I'm just curious because the math is just like a system that we came up, right? It's just like, what if the complex number system were originally included?
As far as I know, it wasn't when I think about math and math's history, the first thing that we used math for was counting. How many pigs and goats and things do you owe the other tribe or whatever it is? I don't know, like stuff like that. I think way back in history land, Was it always there? I don't think it was. So I think this was added after the fact and as we discover more different ways to think about things. Okay? So what we are going to do is we are going to go with the definition that the square root of negative 1 is going to be represented by the letter I, lowercase I. Lowercase I stands for imaginary number. I squared will equal negative 1 by definition. So, let me straighten that out just a little bit. There we go. That's what we're going to do. We're going to be dealing with problems that involve these two facts, and we'll make it more difficult when we get to section 5. When you're simplifying, please take care of the negative first before using any exponents, and don't forget complex numbers like I can be added, subtracted, multiplied, divided with other like terms, but they have to be like terms. Like terms. If there's an I in the denominator, depends if it's a monomial or a binomial, what to do. We're going to talk about what to do in our fourth example. So, I have 4 examples for you to do. 1, 2, 3, 4. Feel free to put these and start your homework on a separate sheet of paper. These can be their top 4 problems, and then you don't have to do them again if you don't want to. They're there as examples. It's up to you. Number 5 says simplify using imaginary numbers. The first thing I want to point out to you is that if you were to try to square root negative 192 on a calculator, your calculator would say this. Math error or syntax error. The reason why? It doesn't exist. It knows there's no real number that I can give you that is the square root of negative 102. So, we are going to break this apart into its imaginary components and its real components. I can think of negative 192 as the same thing as the square root of negative 1 times the square root of 192. And you all should know what the square root of negative 1 simplifies to. Something we just wrote down, maybe right about there somewhere. What is the square root of negative 1? That's what you're going to simplify it as, I. Now what this becomes is a problem that comes from 0.2. Can you simplify the radical? You break down the 192 and you decide 2 goes into there. Is that 96 times? No. Yeah, 96? 2 times 48. Ooh, I know that's a 16 times 3. That'll help me a little bit. And a 4 and a 4. What I'm looking for are pairs of squares. And maybe you know some other factors, but if I find the factors and there's a pair and there's another pair, I can pull those things out. I can pull out the 4 and I can pull out the 2. And as soon as I do, what I'm left with is just the 3 on the inside. I have a 4 times 2 times I times the square root of 3. What does that simplify to? That's 8I root 3. That's what our answer is going to be. Shelton.
So what is the purpose of these equations and its imaginary?
That's a good question. They actually will help us to figure out where a parabola that doesn't cross the x-axis is. They're imaginary solutions. They're above or below the x-axis. I don't know. And maybe that's because I haven't researched enough to figure that out. If you find out, let me know, because I am in the beginning stages of this whole thing. Let's jump to number 16. Number 16, now we're going to be dealing with a problem where we might be adding or subtracting complex numbers. I know this is complex because it has the letter I in it. This is not like an X. This is the imaginary letter I, the square root of -1. This is asking me to subtract this quantity from that quantity. So before I start, the first thing I do is I get rid of parentheses by multiplying anything that's in front. Nothing's in front. So this is just 9 plus 11i. I don't need those parentheses because there's no exponent and there is nothing in front that's multiplying. This negative sign, I'm subtracting this group, so that means that I'm actually need to distribute this negative to the 6 and to the -7i before I can do anything else. After you distribute that negative, then what you can do is you can combine your like terms. 9 minus 6 is 3. That is considered your real component. Your imaginary component is putting together the 11i and the 7i together, which makes 18i. That's your imaginary component. You cannot put these two things together because this is not like terms with that. Your final answer is 3 plus 18i. And standard form, I didn't write this in your notes, but just in case you wanted to know, the standard form of an imaginary number looks like this, where your real component goes first, your imaginary component goes second. It's kind of like this is how they will always write their answer on an SAT or an SBAC or the ACT, in case you ever take those tests. That will help you as you're trying to get into the college of your choice. Very simple questions. This is like, oh, wow, that's easier than 8th grade. Yes, it is. I like it. It doesn't get harder until 12 and 20. So let's do number 12 now. And the first thing that we're going to do with number 12 is we're going to not use the word distribute. because distributive property does not work with an exponent outside of a binomial. This means you have two factors of 5 minus 2i times a 5 minus 2i. We're going to expand our exponent to 5 minus 2i times 5 minus 2i. Yes?
Could you just square root it? So it's just 5
No.
minus 2i?
We don't know what it's equal to. There is no equal sign when we started, so to simplify, we have to expand. Next, we're going to FOIL. We're going to take this 5 and multiply it to the 5, which is no big deal, 25. We're going to do the O in FOIL. We're going to do the 5 times the negative 2i, and that's negative 10i. Then we're going to take the negative 2i times the 5 and get another negative 10i. And then we're going to take the negative 2i times the negative 2i, and that'll be a negative times a negative is a positive. 2 times 2 is 4. I times I is I squared. Where it gets tricky is where you simplify. So what we can do, this isn't the tricky part right here. That's easy. Negative 20i. The 25 is just there. But this 4i squared, we wrote down earlier what I squared was equal to. What is I squared equal to? And, by the way, that's how you go and take an imaginary number and turn it into a real number. Negative 1 is a real number. Imaginary I is an imaginary, but when you square I, it becomes real. It becomes that negative 1. And now we have this 4 is multiplying the I squared. The 4 is multiplying negative 1. Now that 4 is a negative 4. Can that go together with the 25? Let's put those together. What do we get? We get 21 minus 20i. Is that what you got? And I'm putting it in standard form for my answer. The last example that I have for you deals with an imaginary number in the denominator. Our imaginary number in the denominator, you are just like before where you can't have any square roots in your denominator. You'd have to rationalize them. That's the case in the, for this problem. What you're going to have to do is you're going to have to look at the directions that we have right about here. What if there's an I in the denominator? Well, it depends. If the denominator is a monomial, you multiply it by I. If it's a binomial, you need to multiply it by its conjugate, which is the same binomial with a different sign in the middle. Is this a monomial or a binomial? Binomial means two. There are two things here. So it is a binomial. And so we need to multiply by the conjugate. And if you're not sure what the conjugate is in this problem, I'm going to do this for you. This is the same thing. Oh, I thought this was working. There we go. The conjugate is the same thing as the denominator, except a different sign in the middle. You can think of it as it's different of square partner, because that's what it is. Now what this is going to do is this is going to allow us to get rid of the i's in the denominator. You'll see after we FOIL. So let's FOIL the denominator first. 3 times 3? 9. 3 times 2i plus 6i. Negative 2i times 3 is negative 6i. Good thing is those two things cancel. Negative 2i times a positive 2i is negative 4i squared. There's my denominator. My numerator, FOIL, negative 3, minus 2i, plus 15i, plus 10i squared. Simplifying, negative 3 plus 13i, 10i squared. I know what I squared is the same thing as. I'm going to take it from imaginary to a real. That is going to be negative 1. It's multiplying. What does that do to the 10? It makes the 10 negative. Let's put that with the negative 3 when we simplify. I can do the same thing with this 4i squared in the denominator. That makes this negative 1. Negative 1 times that negative 4 makes a positive 4. 9 plus that positive 4 is 13. So what we have now is we have negative 13 plus 13i over 13. And just like the quadratic formula, this is like the whole numerator is divided by 13. Let's split it because this goes into both. And now I know what it simplifies to. Negative 1 plus I. There is no radical in the denominator anymore. Pretty interesting, pretty crazy math. So the last thing that I have to cover is dealing with graphing. And I know I told you that I was going to have you write this stuff down, but instead we're going to read it so I can continue this recording and finish by the time the bell rings. Let's read this together. Complex numbers can be graphed by graphing the real part on the horizontal axis and the imaginary part on the vertical axis. So if you were to try to graph 3 minus 2i, the way you would do that is very simple. This is your real component. You would go 3 units to the right. This is your imaginary component. You would go 2i units down, or just 2 units down. And this dot right here is 3 minus 2i. To figure out what the absolute value is, you would find this distance that goes from here to there by using the Pythagorean theorem. That's all you have to do. So, if you did not get the major part of this, your real part is your x-axis. Nothing changes what's real. Your imaginary is your y-axis. That's your key point. So let me give you an example. It's like 26. 26 says, plot each complex number in a separate complex plane. Meaning, here's my complex plane. Then give its absolute value. There is a real component, and then there's an imaginary component. A plus bi. This is your real component. This is your imaginary component. That means your real component is on your x-axis. What's the real component of number 26? So I'm going to go to the left, and I'm going to be efficient, and I'm going to count by 8s. I'm going to go to the left 8 units, and it's be negative 8 units. Some people say that's lazy. I just say it's efficient. I'm counting by 8 units. My imaginary axis is the vertical one. And what is the imaginary component? Do I go up or down? So I'm going to label this as 6i units technically. We're going to go down 6. So the point, this is the point, negative 8. negative 6i. You can almost think of those two things as an x-coordinate and a y-coordinate. It's what they are. That answers the first part of the question. Plot each complex number in a separate complex plane. Then it says, give its absolute value. The absolute value is the only one that we didn't really talk about. It's just the distance of the object. It's just the Pythagorean theorem on that distance. We just take the a, we square, we take the b, we square, we add it up and square root. What does that mean? That means if I need to find this distance, I'm going to do the Pythagorean theorem on this distance and the Pythagorean theorem on this distance. And notice you can ignore the I when you're doing the b squared. I just do negative 8 squared in parentheses plus negative 6 squared in parentheses, and I take the square root of that. And that is going to be the same thing as the absolute value of negative 8 minus 6i. I know what negative 8 squared is, 64. I know what negative 6 squared is, 36. I know that is the same thing as the square root of 100, and so the absolute value of this whole thing is the same thing as 10. It's the distance, which makes sense because 6, 8, 10 is a Pythagorean triple. Let me put a box around that. We'll stop the recording right here.